Imagine waking up to not one sunrise, but two. Two stars climbing above the horizon, casting double shadows across an alien landscape. One sun larger and golden, the other smaller and orange, locked together in an eternal gravitational dance. As they rise, they paint the sky in colors Earth has never known. Crimson blending into amber, violet shadows stretching across plains of ice or seas of liquid methane. This isn't science fiction, this is real. 1600 light years from Earth, there exists a world that orbits not one star, but two. A planet where the concept of day and night becomes something far stranger than we've ever experienced. Where the sun, or rather, the suns, trace complex patterns across the sky. Where seasons might last for decades or centuries. Where twilight could stretch on forever, depending on where you stand. They were wrong. Not only do these planets exist, but we've discovered dozens of them. And some of them might be capable of supporting life that evolved under two suns, adapted to conditions we can barely imagine. What would it be like to live on such a world? How do you measure time when your planet's orbit is a gravitational ballet around two moving partners? What kind of life could emerge in the twilight zones between eternal day and endless night? Stay with me, because the answers will change how you think about the universe and our place in it. Welcome back to the channel. If you're new here, you've just entered a deep exploration of one of the most fascinating discoveries in modern astronomy. And if you're returning, thank you for joining me once again as we venture into the cosmos. Today, we're going to spend the next 2 hours exploring something that sounds like it came straight from the imagination of a science fiction writer. Planets that orbit two stars instead of one. Binary star systems with worlds trapped in their gravitational embrace, experiencing day-night cycles and seasons unlike anything in our solar system. This isn't a quick overview. This is a comprehensive journey through the science, the discovery, the implications, and the profound questions these worlds raise about the nature of planetary systems and the possibility of life beyond Earth. We'll start with the moment astronomers first confirmed that circumbinary planets could exist, defying decades of theoretical predictions. We'll dive deep into the physics of binary star systems, how two stars orbit each other, how that affects the space around them, and how planets can possibly form in such chaotic environments. We'll explore what life would actually be like on these worlds, the complex dance of light and shadow, the bizarre seasons, the temperature extremes, the unique challenges any life would face. We'll examine the cutting edge of habitability science, asking whether these twilight worlds could support life and what that life might look like. We'll discuss the latest discoveries, the ongoing debates, and the missions planned to study these systems in greater detail. And we'll confront the philosophical implications. If life can exist on a planet with two suns, in an environment radically different from Earth, what does that tell us about how common life might be in the universe? This is the kind of deep dive you can settle in with, whether you're actively watching or letting your mind wander through the cosmos while you work or relax. Every chapter builds on the last, creating a complete picture of these extraordinary worlds. So get comfortable, grab a drink, and prepare to see the universe in a new light, or rather in two lights, dancing together across alien skies. Let's begin. Our story begins with a telescope, a distant star, and a shadow that shouldn't exist. The year was 2011. NASA's Kepler space telescope had been staring at the same patch of sky for 2 years, monitoring the brightness of over 150,000 stars simultaneously. Its mission was simple in concept but revolutionary in execution. Detect planets around other stars by watching for the tiny dimming that occurs when a planet passes in front of its star. The transit method, as it's called, is elegantly straightforward. Imagine holding a coin at arm's length in front of a streetlight. The coin blocks a small fraction of the light. If someone on the other side was measuring the streetlight's brightness with extreme precision, they'd detect a slight dimming while the coin crosses in front. Planets do the same thing to their stars. When a planet transits, crosses in front of the star, from our perspective, the star appears slightly dimmer. The amount of dimming tells us the planet's size relative to its star. The frequency of transits tells us how long the planet's year is. It's a technique that has revolutionized our understanding of planetary systems. But on September 15, 2011, a team of astronomers led by Lawrence Doyle and William Welsh published a paper in the journal Science that announced something nobody expected. They'd found a planet designated Kepler 16b, orbiting not one star, but two. The star system, Kepler 16, was already known to be a binary, two stars orbiting their mutual center of gravity. The primary star is about 69% the mass of our Sun, what astronomers call a K-type main sequence star, glowing orange. Its companion is much smaller, only 20% the Sun's mass, an M-type red dwarf. These two stars orbit each other once every 41 days, separated by just 0.22 astronomical units. That's less than a quarter of the distance from Earth to the Sun. They're close, gravitationally locked in an eternal dance. When Kepler observed this system, it detected the expected eclipses. Every 41 days, one star would pass in front of the other, causing the combined light to dim. This is called an eclipsing binary, and they are common in astronomy. Nothing unusual there. But then the telescope detected additional dips in brightness, smaller ones, regular ones, occurring on a different period than the binary eclipses. At first the team was cautious. False positives are common in transit detection. Instrumental artifacts, background stars, even cosmic rays hitting the detector can create signals that look like planetary transits. The team needed to rule out every other possibility. They analyzed the timing of the dips. They measured their depth and duration. They built models of the system's geometry. And eventually the conclusion was inescapable. There was a third body in the system, a planet. Kepler 16b completes one orbit around both stars every 229 days, about 7.5 months. It orbits at a distance of 0.7 astronomical units from the center of mass of the binary system. To put that in perspective, that's roughly the distance Venus orbits from our Sun, except this planet is circling two stars instead of one. The planet itself is about the size of Saturn, roughly 8.5 times Earth's radius, with a mass about a third of Jupiter's. It's a gas giant, composed primarily of hydrogen and helium, with no solid surface to stand on. The average temperature is estimated at around 100 to 70 degrees Celsius, making it a cold, inhospitable world by human standards. But none of that mattered compared to the sheer fact of its existence. For decades, theoretical models had suggested that planets in closed binary systems were unlikely. The gravitational perturbations from two stars in close orbit should destabilize planetary formation. As the protoplanetary disk, the swirling cloud of gas and dust from which planets form, tries to coalesce into solid bodies, the gravitational tugs from two stars should tear it apart. Picture trying to build a sandcastle while two people walk around you in circles, kicking sand everywhere. That's what planetary formation in a binary system should be like. The constant gravitational interference should prevent planets from ever getting large enough to survive. Yet here was Kepler 16b, fully formed, stable in its orbit, completely defying theoretical expectations. The discovery sent shock waves through the astronomical community. If circumbinary planets could exist around Kepler 16, they could exist around other binary systems. And binary stars are extraordinarily common. Nearly half of all Sun-like stars exist in binary or multiple star systems. This meant that the number of potential planetary systems in the galaxy had just increased dramatically. Billions of binary stars, each potentially hosting planets. The universe was suddenly more crowded with worlds than we'd imagined, but Kepler 16b was just the beginning. In the months and years that followed, Kepler discovered more circumbinary planets. Kepler 34b and Kepler 35b, announced in 2012. Kepler 38b, Kepler 47b and c, Kepler 64b, the list grew. Each discovery reinforced the same stunning conclusion. Circumbinary planets aren't rare oddities. They're a natural outcome of planet formation. Nature finds a way, even in the most chaotic environments. Let me put this in perspective. In our solar system, we have one star, the Sun, and 8 planets orbiting it in relatively circular, stable orbits. The system is orderly, predictable, We can calculate planetary positions thousands of years into the future with incredible accuracy. But in a circumbinary system, everything is more complex. The planet isn't orbiting a stationary point. It's orbiting around two stars that are themselves moving in an elliptical orbit around their mutual center of mass. The gravitational pull on the planet changes constantly depending on where the stars are in their orbit relative to each other and to the planet. Imagine trying to orbit around two people who are spinning around each other on an ice rink. As you try to circle them, they're never in the same position relative to you. Sometimes they're close together, sometimes far apart. The center point you're trying to orbit keeps shifting. It's a three-body problem, one of the most notoriously difficult calculations in physics. For a planet to maintain a stable orbit in such a system, it needs to orbit far enough from the binary pair that the two stars can be treated as essentially a single gravitational source. This creates what astronomers call the circumbinary habitable zone, the region where orbits are stable and potentially where liquid water could exist on a planet's surface. For Kepler 16, that zone exists. The planet orbits well outside the danger zone where gravitational chaos would tear it apart. It's in a stable region where it can complete orbit after orbit without being ejected from the system or crashing into one of the stars. But here's what's remarkable. Kepler 16b orbits very close to the inner edge of the stable zone. It's about as close to the binary pair as a planet can get and still maintain a stable orbit over millions of years. Any closer and the orbit would become chaotic, potentially ejecting the planet into interstellar space or sending it plunging into one of the stars. Why did it form there? Was it born in that location, or did it migrate inward from farther out? How did it manage to survive the violent early period of planetary system formation when collisions and migrations are common? These questions haunted astronomers, because if Kepler 16b could exist in such a precarious orbit, what other unlikely configurations might be possible? The discovery also revived interest in an old question. Could planets in binary systems support life? Kepler 16b itself is a gas giant, incapable of hosting life as we know it. It has no solid surface, and its temperature is far too cold for liquid water. But if Kepler 16b had moons, and gas giants in our solar system have many moons, those moons could potentially be habitable. Or more intriguingly, what if there are rocky planets in other circumbinary systems, orbiting within the habitable zone where temperatures are right for liquid water? The search began. Astronomers started examining every binary star system Kepler had observed, looking for additional transits, additional worlds, and they found them. Not just gas giants, but smaller planets too, some potentially rocky, some in or near the habitable zone. Each discovery added a new piece to the puzzle. Each one raised new questions about how these planets formed, how their climates work, whether they could support life. But to understand these worlds, we need to first understand binary stars themselves, because the nature of the stars determines everything: the environment, the radiation, the stability of planetary orbits, the possibility of life. So let's zoom out for a moment and explore what binary star systems really are, how they form and why they're so common in our galaxy. And in binary stars. The term sounds exotic, but the reality is that they're everywhere. Look up at the night sky, and many of the stars you see aren't solitary like our sun. They're pairs locked together by gravity, orbiting around their mutual center of mass. Sirius, the brightest star in the night sky, is actually two stars, Sirius A and its faint white dwarf companion, Sirius B, Alpha Centauri. Our nearest stellar neighbor is a triple system with three stars bound together. Even Polaris, the North Star, has at least two stellar companions. In fact, surveys of nearby sun-like stars suggest that roughly 40 to 50% exist in binary or multiple star systems. For more massive stars, the percentage is even higher, perhaps 70% or more. Binary and multiple star systems aren't the exception. In many ways, they're the rule. So why are binary stars so common? To answer that, we need to go back to stellar birth. Stars form in giant molecular clouds, vast regions of space filled with gas and dust. These clouds can be hundreds of light years across, containing enough material to form thousands or even millions of stars. Within these clouds, denser regions begin to collapse under their own gravity. As a cloud region collapses, it fragments into smaller clumps. Each clump will potentially become a star or a stellar system. Here's the key. These collapsing clumps often have angular momentum. They're rotating. As the clump contracts, conservation of angular momentum causes it to spin faster, just like a figure skater spins faster when pulling in their arms. This rotation causes the collapsing clump to flatten into a disk. Material falls inward toward the center, where pressure and temperature rise until nuclear fusion ignites and a star is born. But if the original clump had too much angular momentum, or if it was irregularly shaped, or if it fragmented during collapse, you don't get just one star. You get two or more, each forming from a separate density peak in the original cloud. These protostars are born close together, and their mutual gravity keeps them bound. They settle into orbits around their mutual center of mass, and a binary star system is created. The properties of binary systems vary enormously. Some binaries have stars separated by hundreds or thousands of astronomical units, orbiting each other over thousands or millions of years. These are called wide binaries, and their stars barely influence each other. Each star has its own planetary system, and those systems are essentially independent. But other binaries are much closer. The stars might be separated by just a few stellar radii, orbiting each other in days or even hours. These close binaries are where things get interesting and complicated. In close binaries like Kepler 16, the two stars significantly affect each other. Their gravity distorts each other's shapes, pulling them into slight egg shapes. Material can transfer from one star to the other if they're close enough, and most importantly, for our story, their combined gravitational field creates a complex environment that shapes how planets can form and survive. Let's talk about orbital mechanics for a moment, because understanding how binary stars orbit each other is crucial to understanding circumbinary planets. In a binary system, both stars orbit around a point called the barycenter, the center of mass of the system. For two equal mass stars, the barycenter is exactly halfway between them. But if one star is more massive than the other, the barycenter is closer to the more massive star. Imagine two figure skaters holding hands and spinning. If they have equal mass, they rotate around a point halfway between them. But if one skater is much heavier, the lighter skater does most of the moving, while the heavier one barely moves. The center point they rotate around is much closer to the heavier skater. This is where the concept of stable and unstable zones comes in. Through decades of numerical simulations and mathematical analysis, astronomers have identified regions where planetary orbits are stable over long timescales. There are three main types of stable orbits in a binary system. First, a planet can orbit very close to one star, essentially ignoring the other star's gravity because it's so far away. These are called S-type or satellite orbits. The planet is a satellite of one star, just like planets in our solar system are satellites of the Sun. Second, a planet can orbit far from both stars, treating them as essentially a single gravitational source. These are P-type or circumbinary orbits. The planet orbits around the entire binary system. Third, and much less stable, a planet can orbit at one of the Lagrange points, special locations where the gravitational forces of the two stars balance. These orbits are generally unstable over long periods, and we haven't found planets in such configurations. Kepler 16b is in a P-type orbit. It's a true circumbinary planet orbiting both stars, and its orbital distance is just beyond the critical threshold for stability. Simulations show that if it were just 10 to 20% closer to the binary pair, its orbit would become chaotic within a few million years. This raises a fascinating question. Why do circumbinary planets seem to cluster just outside this stability boundary? It's not just Kepler 16b. Most of the circumbinary planets we've discovered orbit very close to the inner edge of the stable zone. One possibility is observational bias. Planets that orbit closer to their stars transit more frequently and are easier to detect. If circumbinary planets were common farther out, we might simply not have observed them yet because their orbital periods are too long, but another possibility is that this clustering is real, and it tells us something about how these planets form. Perhaps they form farther out, where the protoplanetary disk is more stable, and then migrate inward, stopping at the edge of the stable zone. Or perhaps the gravitational interactions during the early, chaotic phase of planetary system formation naturally clear out the inner regions, and planets can only survive if they form or migrate to just beyond the danger zone. We don't have definitive answers yet, but the clustering is suggestive. It's one of many puzzles that circumbinary planets present. Now let's think about what it would actually be like to live on a world orbiting two stars. Not Kepler 16b itself, it's a gas giant with no surface. But imagine a rocky moon orbiting Kepler 16b, or a rocky planet in a similar system. The sky would be utterly unlike Earth's. Instead of one sun following a predictable path across the sky, you'd see two suns, moving relative to each other as they orbit their mutual center. Sometimes the two suns would be close together in the sky, appearing almost as a single bright object. At other times they'd be separated, one rising while the other is setting, creating a prolonged twilight, where the sky is lit from multiple directions. Shadows would be strange. When both suns are above the horizon, every object casts two shadows, one from each star. These shadows shift and move relative to each other as the suns move across the sky. At certain times, the shadows might align, creating a single darker shadow. At other times, they'd point in completely different directions. Eclipses would be more common and more complex. On Earth, a solar eclipse occurs when the moon passes directly between Earth and the sun. On a circumbinary planet, eclipses occur when one star passes in front of the other, from your perspective. Depending on your location on the planet and the orbital alignments, you might see one star completely blocking the other, or partial eclipses, where one star only partially covers its companion. The amount of light and heat the planet receives would vary in complex ways. Not just the day-night cycle we're familiar with, but also variations depending on where the stars are in their mutual orbit. When the two stars are on the same side of the planet, both providing light and heat simultaneously, the planet receives maximum energy. When they're on opposite sides, the planet receives less total energy. And during eclipses, when one star blocks the other, the energy drops even more dramatically. This creates climate and seasonal patterns utterly unlike Earth's. Seasons on Earth are caused by the tilt of our axis relative to our orbit around the Sun. In a circumbinary system, you still have that effect, but layered on top are the variations caused by the binary orbit. A circumbinary planet might have multiple types of seasons. There's the axial tilt seasons, like Earth's, but there's also binary seasons, periods of the year when the planet receives more or less total radiation depending on the binary's orbital configuration. Imagine summer being made more intense because it coincides with the period when both stars are providing maximum combined light, or winter being brutally cold because it occurs during a phase when the stars are eclipsing each other frequently, reducing the total energy received. The complexity is staggering, and it raises profound questions about whether life could adapt to such an environment. On Earth, life is exquisitely adapted to our planet's regular 24-hour day and predictable seasonal cycle. Plants evolved to use photosynthesis tuned to the sun's spectrum. Animals evolved circadian rhythms synchronized to day and night. Migration patterns and hibernation cycles are timed to seasonal changes. Could life adapt to the irregular patterns of light and heat on a circumbinary planet? Could plants photosynthesize with two stars of different colors and brightness? Could animals develop biological clocks that account for complex multi-period cycles? Or would the complexity make life impossible? Is there a threshold of environmental variability beyond which life cannot establish a foothold? These aren't just academic questions, they go to the heart of how common life might be in the universe. Because if half of all stars are in binary or multiple systems, and if circumbinary planets are common, then billions of potentially habitable worlds might be circumbinary. If life can't survive the complexity of two sun systems, we've just ruled out half the galaxy as a potential home for life. But if life can adapt, if it's robust enough to handle these challenges, then the galaxy might be teeming with life in places we hadn't seriously considered. So which is it? To answer that, we need to dive deeper into the specifics of habitability in circumbinary systems. We need to understand what habitability really means, how we calculate it, and whether the peculiar conditions of two sun planets help or hinder the emergence of life. Habitability. It's a word we throw around casually in astronomy. But what does it actually mean? In its most basic definition, a habitable planet is one that can support liquid water on its surface. Liquid water is the key. Not ice, not water vapor, but liquid. The state that serves as the universal solvent for biochemistry as we know it. This definition leads to the concept of the habitable zone, sometimes called the Goldilocks zone, the range of orbital distances from a star where a planet's surface temperature is right for liquid water to exist. Not too hot, not too cold, just right. For our Sun, the habitable zone extends roughly from 0.95 to 1.37 astronomical units. Venus is just inside the inner edge, Earth is comfortably in the middle, and Mars is near the outer edge. These boundaries aren't precise. They depend on atmospheric composition, greenhouse effects, planetary albedo, and many other factors. But they give us a starting framework for thinking about where to search for potentially habitable worlds. Now extend this concept to a binary star system, and everything becomes more complicated. In a binary system, you don't have one star providing a steady amount of heat and light. You have two stars, each with its own luminosity, each contributing to the total energy the planet receives. And because the stars orbit each other, the total energy the planet receives varies over time. Let's use Kepler 16 as an example again. The primary star has about 69% the Sun's mass and produces about 18% of the Sun's luminosity. It's a K-type star, cooler and dimmer than the Sun. The secondary is even smaller and dimmer, an M-type red dwarf with about 20% the Sun's mass and only about 1% of the Sun's luminosity. Combined, these two stars produce about 19% of the Sun's total light output. That's a dim system compared to our own. For a planet to be warm enough for liquid water, it needs to orbit much closer than Earth does to the Sun. But the stars orbit each other every 41 days, and their orbits are slightly elliptical. This means the distance between them changes over time, which affects how much total light they produce toward the planet. When the two stars are at their closest approach to each other, they both contribute maximally to heating the planet. When they're at their farthest separation, the planet receives slightly less total energy because the stars are more spread out from its perspective. Additionally, eclipses matter. When one star passes in front of the other from the planet's viewpoint, the total light drops. For a close binary like Kepler 16, eclipses happen every orbital period. Every 41 days, the system experiences two eclipses as each star passes in front of the other. During a total eclipse, when the primary completely blocks the secondary star, the planet loses that 1% contribution from the secondary. It's not a huge change, but is measurable. During a partial eclipse, the light reduction is less dramatic, but still present. These fluctuations create a time-variable habitable zone. Unlike our solar system, where the habitable zone is basically a fixed range of distances, in a binary system, the habitable zone shifts slightly inward and outward depending on the binary orbital phase. For a planet to be stably habitable in such a system, it needs to remain within the habitable zone throughout all these variations. It can't be on the edge, where binary orbital variations push it alternately too hot and too cold. It needs to be firmly in the middle, where even the minimum energy received is sufficient for liquid water. This narrows the habitable zone in binary systems. You can't use the edges, only the core region, where temperatures remain stable despite the variations. For Kepler 16, calculations suggest the habitable zone extends from about 0.5 to 1.0 astronomical units from the system's center of mass. Kepler 16b orbits at 0.7 AU, which puts it right in the middle of this range. Wait, does that mean Kepler 16b is habitable? Not exactly. Remember, Kepler 16b is a gas giant, a Saturn-sized planet with no solid surface. Its atmospheric temperature is far below freezing. The planet itself isn't habitable for life as we know it. But here's where it gets interesting. Kepler 16b could have moons, and those moons could potentially be habitable. In our solar system, Jupiter and Saturn have large moons, some of which are geologically active and have subsurface oceans. Europa, Enceladus, Titan, these moons are considered among the most promising places to search for life in our solar system. If Kepler 16b has Earth-sized or Mars-sized moons orbiting it, those moons would be subject to the same radiation environment as the planet. They'd be in the habitable zone. And if they have the right atmospheric composition and geological activity to maintain liquid water on their surfaces, they could be habitable worlds. Imagine that, a moon orbiting a gas giant, which orbits two suns. From the surface of such a moon, the sky would be even more complex. You'd see two suns moving across the sky, plus the massive bulk of your parent planet, which would go through phases like our moon does. Sometimes a full disk reflecting sunlight, sometimes a crescent, sometimes blocking one or both suns in a spectacular eclipse. It's a dizzying thought, but it's physically plausible. And it might be common, but moons of gas giants aren't the only possibility. What about rocky planets in their own circumbinary orbits? Several of the circumbinary planets discovered by Kepler are smaller than Kepler 16b. Kepler 47c, for instance, is about 4.6 times Earth's radius, large, but potentially a mini-Neptune with a rocky core, or even a super-Earth if it's dense enough. Kepler 47c orbits in the habitable zone of its binary star system. Its year is 303 days, longer than Earth's. The system's two stars are similar in mass ratio to Kepler 16, but their combined luminosity is different, creating a different habitable zone. Could Kepler 47c be habitable? We don't know enough about its composition. If it's a mini-Neptune with a thick hydrogen-helium atmosphere, probably not. But if it's a water world or a super-Earth with a thin atmosphere, it might be. This is one of the great frustrations of exoplanet science. We can detect these planets, measure their size and orbital period, but we often can't determine their composition or whether they have atmospheres suitable for life. That's changing. The James Webb Space Telescope and future missions will allow us to study the atmospheres of some of these worlds, looking for biosignatures, gases like oxygen, methane, and water vapor that might indicate biological activity. But for now, we're left with possibilities. Tantalizing, frustrating possibilities. Let's talk about the challenges life would face on a circumbinary planet, because they're significant. First, there's the variability of radiation. Life on Earth is adapted to a very stable energy input from the Sun. Our Sun is a main sequence star in a stable phase of its life, and its output varies by less than 0.1% over short timescales. On a circumbinary planet, the total energy received varies much more. Not dramatically, perhaps a few percent, but consistently, and on multiple timescales. The binary orbital period creates a short-term cycle of radiation variation. The planet's own orbital period creates a longer-term cycle, and if the planet's orbit is elliptical, there's an additional variation as it moves closer and farther from the stars. Plants on Earth rely on predictable seasonal patterns to time their growth, flowering, and dormancy. Could plants on a circumbinary planet adapt to multi-period cycles? Would they need more complex biological clocks? Or would they simply need to be more generalist, able to photosynthesize across a wider range of conditions? Second, there's the issue of orbital stability over evolutionary timescales. We know circumbinary planets can have stable orbits over millions of years. The numerical simulations confirm this. But life requires billions of years to evolve from simple chemistry to complex organisms. On Earth, it took about 3.5 billion years for complex multicellular life to emerge, and 4.5 billion years total for intelligent life to appear. for complex life to evolve on a circumbinary planet, the orbital environment needs to remain stable for similarly long periods. Are circumbinary orbits stable over billions of years? For most systems, the answer seems to be yes, as long as the planet orbits far enough from the binary. But there are edge cases where long-term perturbations could accumulate, gradually destabilizing the orbit. Third, there's the question of atmospheric retention. Planets orbiting close to their stars, even in the habitable zone, are subjected to intense stellar winds and radiation. This can strip away atmospheric gases over time, especially lighter gases like hydrogen and water vapor. In a binary system with two active stars, the radiation environment might be more harsh. If either star experiences frequent flares, common in red dwarfs, the planet could be bombarded with high-energy particles that damage the atmosphere and potentially harm any surface life. On the other hand, binary systems might have advantages too. For one, the combined radiation from two stars provides more total energy, even if each star is dim. A planet in a binary system might be able to orbit farther from the stars than an equivalent planet around a single star, giving it more orbital space and potentially more stable, long-term dynamics. Additionally, the presence of two stars might create unique niches for life. On Earth, different organisms are adapted to different light conditions: full sun, partial shade, deep ocean. On a circumbinary planet, the dual shadows and complex lighting could create even more diverse ecological niches, driving evolutionary innovation. Some scientists have speculated that circumbinary planets might actually be more favorable for life than single-star planets, precisely because of their complexity. Life thrives on energy gradients and environmental variability. Too much variability is destructive, but some variability drives adaptation and evolution. A circumbinary planet with moderate variations in radiation might provide just the right level of environmental challenge to promote biological diversity without overwhelming life's ability to adapt. It's a controversial idea, and we won't know if it's true until we actually find life on such a world. But it's a reminder that habitability isn't just about having liquid water. It's about the entire environmental context. The radiation, the orbital dynamics, the atmospheric composition, the geological activity, and in circumbinary systems, that context is unlike anything we experience on Earth. So could life exist on a circumbinary planet? The answer, frustratingly, is maybe. The physics doesn't rule it out, the chemistry should work, the energy is there. But the details matter. A planet needs to be in the right orbit, with the right atmosphere, around the right pair of stars. Too close and it's fried. Too far and it's frozen. Too much atmospheric stripping and it becomes a barren rock. Too much variability in radiation, and life can't establish stable ecosystems. Somewhere out there, among the billions of binary systems in the galaxy, there are probably circumbinary planets that thread the needle. Worlds where conditions are just right for life to emerge and thrive. The question is, how common are they? And how do we find them? Let's step out of the abstract and into the specific. Let's imagine what it would actually be like to experience time on a circumbinary planet. Time on Earth is measured by rhythms. The day, the rotation of Earth on its axis, 24 hours from sunrise to sunrise. The year, Earth's orbit around the sun, 365 days from summer to summer. These rhythms define our lives. They govern sleep and wakefulness, agriculture and seasons, culture and calendar. On a circumbinary planet, time becomes more complex. Consider first a day. Just like Earth, a circumbinary planet rotates on its axis. If the planet has an Earth-like rotation period, say 24 hours, then you'd experience sunrise and sunset at familiar intervals. But sunrise on a circumbinary planet is different. Instead of one sun appearing over the horizon, you might see two. Depending on where the stars are in their mutual orbit, they might rise together, appearing as a bright double star. Or they might rise separately, one sun climbing into the sky hours before its companion follows. Imagine waking up to the first sun rising, casting golden light across the landscape. The world brightens, shadows appear. Then, a few hours later, the second sun rises, and suddenly every shadow splits in two. The light intensifies. Colors shift as the combined spectrum of both stars illuminates the world. As the day progresses, the two suns arc across the sky at different speeds or angles, depending on the geometry of their orbits. One might pass overhead, while the other skims the horizon. Or both might converge toward the zenith, creating a brief period of maximum brightness and heat. Sunset reverses the process. One sun sets first, and the world shifts to the light of a single star. Shadows merge back into one. Colors change again. Then finally the second sun sets, and night falls. Except night might not be fully dark. If the planet's orbit and rotation are aligned in certain ways, one sun might set just as the other is about to rise, creating perpetual twilight in some regions or seasons, a world where true darkness never comes, where the sky always holds at least a faint glow from one star or the other. This is what I mean by endless twilight. Depending on latitude, season, and the orbital configuration, there could be regions of circumbinary planets where the sun never fully sets or never fully rises, creating zones of permanent twilight. Now let's think about the year. On Earth, a year is the time it takes to complete one orbit around the sun. Seasons result from Earth's axial tilt. As we orbit, different hemispheres tilt toward or away from the sun, creating summer and winter. On a circumbinary planet, the year is measured by one complete orbit around both stars. Kepler 16b's year is 229 Earth days. Kepler 47c's year is 303 days. These are comparable to Earth's year, but other circumbinary planets might have much longer or shorter years. But here's the complication. The binary stars themselves are orbiting each other. In Kepler 16, the stars complete one mutual orbit every 41 days. This creates a second rhythm, a binary period that affects the planet. Think of it this way. As the planet orbits the binary pair, it's also watching the stars orbit each other. From the planet's perspective, the two stars are constantly changing their configuration. Sometimes they're close together in the sky, sometimes far apart, sometimes eclipsing each other. This means the amount of total light the planet receives varies, not just with its own orbital position, but also with the binary phase. Even if the planet is at a fixed distance from the binary system's center of mass, the apparent brightness and heat vary as the stars move relative to each other. Imagine a year on such a world. Let's say you're on a rocky moon of a gas giant in a Kepler 16-like system. Your year is 229 days. The binary period is 41 days. As your world completes its orbit, you'd experience roughly 5.5 binary periods per year. Each binary period brings a cycle of changing light levels as the stars move relative to each other and eclipse. This creates a complex pattern. Some parts of your year would coincide with binary phases, where both stars are contributing maximum light. Let's call these bright phases. Other parts of your year would coincide with frequent eclipses, dim phases. If your planet also has axial tilt, and most planets do, then you're layering this binary variation on top of traditional seasonal changes. Imagine this, you're in the northern hemisphere of your world, and it's the beginning of spring. The northern hemisphere is just starting to tilt toward the suns. At the same time, the binary is entering a bright phase. Both stars are nearly aligned from your perspective, providing maximum combined light. Spring is warm and bright, more so than usual. Plants burst into bloom, taking advantage of the abundant light. Animals emerge from hibernation or give birth, timing their reproduction to this favorable period. As spring turns to summer, your hemisphere tilts fully toward the suns. Normally, this would be the hottest time of year. But now, the binary enters a dim phase. The stars are eclipsing each other more frequently, reducing the total light. Summer is cooler than expected. Instead of scorching heat, you get pleasant warmth. Fall begins, and your hemisphere starts tilting away from the suns. But the binary cycle shifts back to a bright phase. The autumn is unusually warm, warmer than spring was, even though the axial tilt would normally make it cooler. Harvest is abundant. Winter arrives and the binary cycle again enters a dim phase. Your hemisphere is tilted away and the stars are eclipsing. It's the coldest time of year. colder than any winter in recent memory. Snow and ice dominate. Life hunkers down to survive. And then the cycle repeats, but not exactly. Because the binary period, 41 days, and the planetary year, 229 days, don't divide evenly. The phase relationship shifts each year. The next year, spring might begin during a dim phase instead of a bright phase. Winter might coincide with bright phases, making it milder. Over several years, the pattern cycles through all possible combinations. Some years have brutal winters and mild summers. Other years have scorching summers and temperate winters. The exact pattern repeats only after several years, when the binary cycle and planetary year realign. This is what I mean by complex seasons. It's not just hot and cold following a simple annual pattern. It's multiple overlapping cycles, creating intricate variations that repeat on multi-year timescales. For any life trying to survive on such a world, adaptation would be challenging. How do you time reproduction when favorable conditions don't occur at the same time each year? How do you hibernate when winter's severity varies unpredictably? Perhaps life would evolve generalist strategies. Organisms that can survive a wide range of conditions rather than specializing for particular seasons. Or perhaps biological clocks would evolve to track multiple rhythms simultaneously, predicting both axial tilt seasons and binary phase variations. On Earth, many animals have circadian rhythms, internal clocks that track the 24-hour day. Some also have circannual rhythms, internal clocks that track the yearly cycle. On a circumbinary planet, organisms might evolve trirhythmic clocks, tracking the day, the year, and the binary period. It sounds implausible, but life is extraordinarily adaptive. Given enough time, evolution finds solutions to the most complex problems. Now let's talk about the twilight zones, regions where the lighting is neither fully day nor fully night, but something in between. On Earth, we experience twilight twice a day, for brief periods after sunset and before sunrise. Civil twilight lasts until the sun is 6 degrees below the horizon, nautical twilight until 12 degrees, astronomical twilight until 18 degrees. On a circumbinary planet, twilight zones can be geographic features, not just temporal ones. Imagine you're near the planet's terminator, the boundary between the day side and night side. On Earth, the terminator is a moving line, sweeping across the surface as the planet rotates. But on a circumbinary planet with two suns, the terminator is more complex. If both suns are above the horizon, you're in full daylight. If both are below, you're in night. But if one is above and one below, you're in twilight, lit by a single sun instead of two. Because the two suns don't move together in the sky, there are regions where one sun is always visible, while the other rises and sets. These regions experience prolonged or even permanent twilight. For example, near the poles, if the planet has axial tilt, you might experience periods where one sun is circumpolar, never setting, just circling the horizon, while the other sun rises and sets normally. For part of the year, you'd live in a world lit by a single, low-hanging sun, casting long shadows at all hours. Or consider a moon tidally locked to its parent gas giant in a circumbinary system. One hemisphere always faces the planet, the other always faces away. The planet-facing hemisphere sees the gas giant dominate the sky, occasionally eclipsing one or both suns. The far hemisphere never sees the planet. For inhabitants of the planet-facing side, day and night are defined not just by the sun's positions, but by whether the giant planet is casting its vast shadow over you. When the planet eclipses both suns, you experience a unique double eclipse darkness. When it eclipses only one sun, you experience planet-shaded twilight. These twilight zones might be the most habitable regions on such worlds. Full daylight might be too hot, with both suns blazing overhead. Deep night might be too cold. But twilight, where temperatures are moderate, where one sun provides steady light, could be the sweet spot for life. Imagine ecosystems adapted specifically to twilight conditions. Plants that photosynthesize efficiently under the single sun spectrum. Animals active during the twilight hours, when predators adapted to bright light or darkness are less effective. On Earth, crepuscular animals, those active at dawn and dusk, occupy a specific ecological niche. On a circumbinary planet, crepuscular regions might dominate the habitable zones. And here's a strange thought. What if intelligent life evolved in these twilight zones? What would their culture be like? Their mythology? Their science? On Earth, human civilization developed around the rhythms of day and night, the cycle of seasons. Our calendars, our agriculture, our sleep cycles, all are tuned to Earth's simple, predictable patterns. But an intelligent species on a circumbinary planet would experience time differently. Their calendars would track multiple cycles. Their festivals and cultural practices would align with complex multi-year patterns. Their mythology would likely feature two suns as central figures, perhaps as deities locked in an eternal dance, sometimes in harmony, sometimes in conflict. And their science would develop differently. Astronomy would be more complex from the start. Understanding their own planet's motion would require grasping three-body dynamics long before developing spaceflight. Their mathematics might be more sophisticated in certain areas, driven by the need to predict the intricate patterns of light and season. It's speculative, of course. We have no idea if intelligent life exists on circumbinary planets, but if it does, it would be shaped by its environment in ways we can only begin to imagine. We've talked about what circumbinary planets are like, but we haven't fully addressed one of the most fundamental questions. How do they form in the first place? Remember, for decades, scientists believed these planets shouldn't exist. The gravitational chaos of a binary star system should prevent planets from forming, and yet here they are. So what's going on? To understand planetary formation in binary systems, we first need to understand how planets form in single star systems like our own. Stars form from collapsing clouds of gas and dust. As the cloud collapses, conservation of angular momentum causes it to flatten into a rotating disk, the protoplanetary disk. The star forms at the center and the disk surrounds it. Within the disk, dust grains collide and stick together through electrostatic forces and eventually gravity. Over time, these grains grow into pebbles, boulders, and eventually planetesimals, objects kilometers in size. Planetesimals collide and merge, forming protoplanets. The largest protoplanets dominate, sweeping up material in their orbital paths. Eventually, you're left with a small number of planets in stable orbits, with most of the disk material either incorporated into planets, blown away by stellar winds, or ejected from the system. This process takes a few million to tens of millions of years. It's well studied, and while there are still details we don't understand, the basic outline is clear. Now, what happens in a binary system? In a closed binary like Kepler 16, both stars form from the same collapsing cloud, likely within the same protoplanetary disk. As they form, their gravity affects the disk structure. The star's gravitational pull clears out material from the inner region of the disk. The area between the two stars and their mutual orbit is swept clean. Material can't stably orbit in this region because of the strong, changing gravitational forces from both stars. This creates a central cavity in the disk. The disk becomes a ring with an inner edge beyond which planetesimals can form. Simulations show that the inner edge of this stable disk is typically about twice the separation of the two stars. For Kepler 16, with the stars separated by about 0.22 AU, the disk's inner edge would be around 0.4 to 0.5 AU. Beyond this edge, the disk should be relatively stable. The two stars can be treated as a single gravitational source, and planetesimal growth proceeds much like in a single star system. This explains why circumbinary planets cluster just outside the stability boundary. They formed where the disk began, at the inner edge of the stable zone. But there's a complication. The gravitational effects of the binary don't just clear out the inner disk. They also affect the entire disk's structure. The binary exerts tidal forces on the disk, causing it to warp and precess, to wobble like a spinning top. These tidal effects can create density waves in the disk, regions of higher and lower density that spiral outward. These density waves can either help or hinder planet formation. On one hand, density enhancements can accelerate planetesimal growth by concentrating material. On the other hand, the constantly changing disk structure can disrupt planetesimal orbits, causing collisions that shatter rather than build. Whether planets can form depends on the balance between these competing effects, and that balance depends on the specific properties of the binary, the stellar masses, the orbital separation, the disk mass, and composition. For binaries like Kepler 16, the balance favors planet formation. The binary is close enough that it clears a central cavity, but not so close that it disrupts the entire disk. The stable region beyond the cavity allows planets to grow. But not all binaries are like this. In very close binaries, where the stars are separated by just a few stellar radii, the tidal effects might be too strong, shredding the disk and preventing planet formation entirely. In very wide binaries, where the stars are separated by hundreds or thousands of AU, each star effectively has its own independent disk, and planets form around each star individually rather than in circumbinary orbits. The circumbinary planets we've discovered exist in a sweet spot. Binaries with separations of roughly 0.1 to 1 AU, where the stars are close enough to create a shared disk environment, but not so close that they destroy it. But here's the mystery. Even in this sweet spot, forming planets is hard. The truncated inner disk has less material available. The tidal forces still create perturbations. And yet, circumbinary planets not only form, they form in substantial numbers. One possibility is that we're only seeing the survivors. Perhaps many circumbinary planetary systems formed, but in most cases, the planets were ejected or destroyed by gravitational interactions. The systems we observe are the rare, stable configurations that endured. This would imply that circumbinary planet formation is inefficient. For every system with surviving planets, there might be 10 systems where planets formed but didn't survive. Another possibility is that circumbinary planets don't form in situ, where we currently find them, but migrate inward from farther out. Planetary migration is a well-established phenomenon. Planets interact with the remaining disk material through gravitational torques. These interactions can cause planets to drift inward or outward over time. In a circumbinary system, a planet forming at, say, 1 or 2 AU could migrate inward, stopping at the inner edge of the stable zone where we observe circumbinary planets today. This would explain why circumbinary planets cluster just outside the stability boundary. They didn't form there, they migrated there, and then halted, because migrating any closer would destabilize their orbits. The challenge with this idea is understanding what stops the migration. In single-star systems, planets can migrate all the way to the star, creating hot Jupiters, gas giants in extremely close orbits. But in binary systems, the inner boundary of the stable zone seems to act as a migration barrier. Some simulations suggest that the disk's inner edge creates a density gradient that halts inward migration. The planet reaches the edge of the disk and can't migrate farther, because there's no more disk material interior to its orbit to interact with. This is an active area of research. Astronomers are running ever more sophisticated simulations, modeling the disk structure, the planet formation process, and the migration dynamics in exquisite detail. And they're finding that circumbinary planet formation might actually be easier than we thought. A recent study suggested that the binary's gravity, while disruptive, also creates regions of enhanced density in the disk where planetesimals can grow rapidly. The same tidal forces that clear the inner disk also compress and focus material in certain locations, accelerating planet formation. In this view, circumbinary planets don't form despite the binary environment. They form because of it. The binary creates conditions that, while chaotic, are also conducive to rapid planetesimal growth. It's a fascinating idea, and it might explain why circumbinary planets seem to be relatively common. If the binary environment actually enhances planet formation in certain ways, then we'd expect many binaries to host planets. But let's not forget, we're still in the early stages of understanding this. Kepler discovered a dozen circumbinary planets. TESS, the Transiting Exoplanet Survey satellite, has found a few more, but that's out of tens of thousands of binary systems observed. Are circumbinary planets truly common? Or are we just seeing the most obvious cases? Systems where orbital geometry aligns such that we can detect transits. The transit method, while powerful, has a huge limitation. It only works if the planet's orbit is aligned nearly edge-on from our perspective. If we're looking at a binary system from above or below the orbital plane, we won't see transits even if planets are present. For single-star systems, this means we detect maybe 1 to 5% of planets through transits. The rest are tilted such that they don't pass in front of their stars from our viewpoint. For circumbinary systems, the geometric requirements are even more restrictive. The planet's orbit must be aligned with the binary orbital plane, and that plane must be nearly edge-on to us. This significantly reduces the probability of detecting circumbinary planets via transits. In other words, for every circumbinary planet we've detected, there could be hundreds we haven't because their orbits aren't oriented correctly for transits. This suggests circumbinary planets might be far more common than current numbers indicate. The dozen or so we've found might be the tip of the iceberg. Future missions will help clarify this. The European Space Agency's Plateau mission, planned for launch in 2026, will monitor hundreds of thousands of bright stars for transits, including many binary systems. Its long observation baseline will allow detection of planets with longer orbital periods, circumbinary planets that take years to orbit and thus transit infrequently. Ground-based surveys are also improving. Radial velocity measurements, detecting planets by the wobble they induce in their stars, are becoming precise enough to detect circumbinary planets. This method doesn't require specific orbital alignment, so it could reveal planets we can't detect via transits. And there's direct imaging. For very wide binaries, where circumbinary planets orbit far from the stars, it might be possible to photograph the planets directly. This is challenging. Planets are faint compared to stars, but advancing technology is making it feasible for larger planets. As these methods mature, we'll build a more complete census of circumbinary planets. We'll learn how common they are, how their properties vary with binary characteristics, and how their formation processes differ from planets in single-star systems. And with that knowledge, we'll be able to answer one of the most profound questions. How many potential homes for life exist in the galaxy? Because if circumbinary planets are common, and if some fraction of them are habitable, then the number of potentially life-bearing worlds is much larger than we've traditionally estimated. It's a thrilling prospect, and it's why astronomers are so excited about circumbinary planets, not just because they're scientifically fascinating, but because they expand the scope of where we might find life. Let's take a tour of the circumbinary planets we've discovered so far. Each one is unique. Each one tells a different story about what's possible in these systems. We've already talked extensively about Kepler 16b, the first confirmed circumbinary planet, but it's worth revisiting because it set the template for everything that followed. Kepler 16b, a Saturn-sized gas giant orbiting two stars every 229 days. It's cold, around 100 degrees on average, and inhospitable to life as we know it. But it proved that circumbinary planets exist and can have stable orbits. It shattered assumptions and opened a new chapter in exoplanet science. From the surface of a hypothetical moon orbiting Kepler 16b, you'd see two suns, one orange, one red, moving across the sky in their 41-day dance. The gas giant would dominate the sky, going through phases like our moon, and during certain alignments you'd witness spectacular triple eclipses, one star eclipsing the other, while both are eclipsed by the planet itself. Darkness in the middle of the day, a cosmic alignment that would have terrified and inspired any civilization witnessing it. Next came Kepler 34b and Kepler 35b, announced in early 2012. Kepler 34b orbits two Sun-like stars, both slightly less massive than our Sun. The planet is about 22% larger than Jupiter and orbits every 289 days. Its orbit places it just outside the habitable zone, too cold for liquid water, but warmer than Kepler 16b. Kepler 35b is similar, a Jupiter-sized planet orbiting two smaller stars every 131 days. Also too cold for life, but another confirmation that circumbinary planets aren't flukes. What's interesting about these two is that they showed circumbinary planets can form around different types of binary stars. Kepler-16 has a K-type primary and M-type secondary. Kepler-34 and 35 have G-type primaries, stars more similar to our Sun. This diversity suggested that circumbinary planet formation isn't restricted to specific stellar types. Then came Kepler-38b, a Neptune-sized planet. At about 435 times Earth's radius, it's substantially smaller than the previous discoveries. Its orbit is just 105 days, and it's much hotter because its binary system is more luminous. Kepler-38b was significant because it showed that circumbinary planets aren't just gas giants. Smaller planets, super-Earths or mini-Neptunes, can also form in these systems. This raised hopes for finding rocky, potentially habitable circumbinary worlds. And then came Kepler-47, and everything changed again. Kepler-47 is a triple-planet circumbinary system, 3 planets orbiting a binary star. When it was announced in 2012, 2 planets were confirmed, Kepler-47b and Kepler-47c. In 2019, a third planet, Kepler-47, was discovered in the same system. Kepler-47b is the innermost planet, about 3 times Earth's radius, orbiting every 49 days. It's hot and likely uninhabitable. Kepler-47d is the middle planet, about 7 times Earth's radius, orbiting every 187 days. It's in the habitable zone, but its size suggests it's probably a mini-Neptune with a thick atmosphere, not a rocky world. Kepler-47c is the outermost planet, about 4.6 times Earth's radius, orbiting every 303 days. It's also in the habitable zone. And here's where it gets exciting. Kepler-47c might be a water world or a super-Earth. If Kepler-47c is a super-Earth, a rocky planet larger than Earth, and if it has the right atmospheric composition, it could potentially support liquid water on its surface. This would make it the first confirmed habitable zone circumbinary planet with even a remote chance of habitability. We don't know enough about Kepler-47c to say definitively. Its mass hasn't been precisely measured, so we can't calculate its density, which would tell us if it's rocky or gaseous. But the possibility is tantalizing. Imagine a rocky world orbiting 2 suns with oceans and continents, life evolving under skies lit by binary stars. It's the stuff of science fiction made potentially real. Kepler-47 also proved that multi-planet systems can exist in circumbinary configurations. The planets don't disrupt each other's orbits. They found stable niches, just like planets in our solar system have. This suggests that circumbinary planetary systems can be just as complex and diverse as single-star systems. They're not limited to 1 or 2 planets. They can have families of worlds, each with its own characteristics. Another notable system is Kepler-4113, discovered in 2014. Kepler-4113b is unusual because its orbital plane precesses, wobbles, over time. Most circumbinary planets have orbits that are well aligned with the binary orbital plane, but Kepler-413b's orbit is tilted and precessing, causing the planet to sometimes transit the stars and sometimes not. This precession means that over an 11-year cycle, the planet's orbit tilts in and out of our line of sight. For a few years, we see transits. Then for several years, we don't because the orbit has tilted away from us. Kepler-4113b demonstrates that circumbinary orbits can be dynamically complex, with long-term changes in orientation. This complexity might be common, but hard to detect. If a planet's precession keeps it out of our line of sight most of the time, we'd never know it's there. Then there's Kepler-453b, notable for being in the habitable zone of its binary system. It's a Neptune-sized planet, so likely not habitable itself, but it shows that planets can stably orbit in regions where temperatures are suitable for liquid water. And there's Kepler-1647b, which holds the record for the largest circumbinary planet discovered by Kepler. It's about 1.5 times Jupiter's radius and orbits every 1,107 days, over 3 years. its long orbital period made it difficult to detect because Kepler only observed 3 transits during its mission. Kepler 1647b's existence proves that circumbinary planets can have long-period orbits, orbiting far from their binary stars. This expands the potential range of environments where these planets exist. Finally, let's talk about TOI 1338b, discovered by TESS in 2019. TOI 1338b is particularly special because it was discovered by a high school intern, Wolf Kukir, while examining TESS data. It's about 6.9 times Earth's radius, orbiting a binary system every 95 days. The discovery demonstrated that TESS is capable of finding circumbinary planets, even though its observing strategy, monitoring fields for only 27 days at a time, makes detecting them more challenging than with Kepler's longer observations. TOI 1338b is located about 1,300 light-years away in the constellation Pictor. Its binary system consists of a Sun-like star and a red dwarf, similar to Kepler 16. The planet orbits in a nearly edge-on configuration, allowing us to see transits clearly. This catalogue of worlds, Kepler 16b, Kepler 34b, Kepler 35b, Kepler 38b, Kepler 47b CD, Kepler 413b, Kepler 453b, Kepler 1647b, TOI 1338b, represents just over a dozen confirmed circumbinary planets. It's a small sample, but it's revealing. These planets come in a range of sizes, from super-Earths to giants larger than Jupiter. They orbit at various distances, from scorching close-in orbits to temperate habitable zones. They exist around binaries with different stellar types and orbital configurations. The diversity is encouraging. It suggests that circumbinary planet formation is a robust process that works across a wide range of conditions. But the sample is also frustrating in what it doesn't tell us. We don't have any confirmed rocky Earth-sized circumbinary planets in habitable zones. The closest candidates, Kepler 47c and Kepler 453b, are too large to be purely rocky, and we lack detailed atmospheric data. We don't know if any of these planets have moons. Gas giants in our solar system have extensive moon systems, some of which might be habitable. Jupiter's moon Europa, Saturn's moon Enceladus, and Saturn's moon Titan are all considered high-priority targets in the search for life. If circumbinary gas giants have similar moons, those could be habitable even if the planets themselves aren't. And we don't have direct images of any of these worlds. Everything we know comes from transit observations, tiny dips in starlight measured across vast distances. We emphasize orbital period and rough temperature estimates, but we can't see the planets directly. This will change. The next generation of telescopes, particularly the James Webb Space Telescope, which is already operational, and future missions, like Plato, will allow us to study these worlds in greater detail. JWST can perform transmission spectroscopy on some circumbinary planets, analyzing the starlight that passes through their atmospheres during transits to identify gases present. This will tell us about atmospheric composition, temperature structure, and potentially even weather patterns. Plato will discover more circumbinary planets, including potentially smaller, rocky ones. Its long observing baseline will enable detection of planets with longer orbital periods, circumbinary planets that take years to orbit and thus transit infrequently. And someday, perhaps in the 2030s or 2040s, we'll have telescopes powerful enough to directly image circumbinary planets, at least the larger ones. We'll see them as actual points of light, separate from their stars. We'll measure their reflected light spectra, search for signatures of clouds, oceans, maybe even vegetation. The circumbinary planets we've discovered so far are pioneers. They're the first representatives of what might be a vast population of worlds orbiting binary stars throughout the galaxy. Each one is a treasure, a window into a type of planetary system radically different from our own. And each one raises questions that drive us to look deeper, to build better instruments, to push the boundaries of what we can observe. Because out there, among the stars, there are worlds we haven't yet imagined. Worlds where twin suns illuminate alien landscapes, where twilight stretches across continents, where life, if it exists, has adapted to rhythms and cycles we're only beginning to understand. We've talked about what circumbinary planets are and how they might form, but now let's dive into the actual physics. What forces shape these worlds? What makes their orbits stable or unstable? And why does the geometry of these systems create such complex patterns of light and shadow? Let's start with orbital mechanics. On Earth, we're used to thinking about orbits as simple ellipses. A planet orbits a star in an elliptical path with the star at one focus of the ellipse. The math is clean, elegant, described by Kepler's laws of planetary motion from the 17th century. But that's only true for a two-body system. One planet, one star. Add a second body, and everything becomes vastly more complicated. The three-body problem is one of the most famous unsolved problems in classical mechanics. Given three objects interacting through gravity, there's no general analytical solution. You can't write down a simple equation that tells you where each object will be at any future time. Instead, you have to resort to numerical simulations, using computers to calculate the gravitational forces at each moment and incrementally step forward in time, tracking how the objects move. For circumbinary planets, we have at least three bodies, two stars, and a planet. In reality, if there are multiple planets, or if the stars have their own planets in S-type orbits, the number of bodies increases, making the problem even more complex. So how do we analyze these systems? The key insight is that in many circumbinary systems, the problem simplifies under certain conditions. If the planet orbits far enough from the binary that the separation between the stars is small compared to the planet's orbital distance, you can approximate the binary as a single point mass located at the system's center of mass. From the planet's perspective, it's essentially orbiting a single, slightly wobbling star. This is called the binary as a point mass approximation, and it works well for understanding the basic orbital dynamics of circumbinary planets. Under this approximation, the planet's orbit is stable as long as it's beyond a critical distance from the binary. That critical distance is roughly 3 times the binary's semi-major axis, the average separation between the two stars. For Kepler 16, where the binary's semi-major axis is 0.22 AU, the stability boundary is around 0.66 AU, and indeed Kepler 16b orbits at 0.7 AU, just beyond this boundary. But the approximation breaks down as the planet gets closer, or if the binary orbit is highly eccentric, or if the planet's orbit is significantly tilted relative to the binary plane. In those cases, you need full three-body simulations to understand the dynamics. These simulations reveal fascinating behavior. Circumbinary orbits can precess. Their orientation in space can slowly rotate over time. The planet's orbit might be slightly elliptical, and the direction of that ellipse's major axis can shift, completing a full rotation over thousands or millions of years. This precession is caused by the asymmetric gravitational pull from the binary. As the stars orbit each other, the planet feels a time-varying gravitational force that tugs on its orbit, causing it to wobble and shift. For most circumbinary planets, this precession is slow and doesn't affect orbital stability. But for some, like Kepler 4.1b, the precession is rapid and significant. Kepler 4.1b's orbital plane tilts back and forth relative to our line of sight on an 11-year cycle, causing its transits to appear and disappear periodically. Now let's talk about tidal forces. Tides are differences in gravitational pull across an object. On Earth, the moon's gravity pulls more strongly on the side of Earth facing the moon than on the far side, creating tidal bulges in the oceans. In a circumbinary system, the planet experiences tidal forces from both stars. When the stars are aligned on the same side of the planet, their tidal forces add together. When they're on opposite sides, the forces partially cancel. This time-varying tidal force causes the planet to flex slightly as it orbits. For a gas giant like Kepler 16b, this flexing dissipates energy as heat in the planet's interior. Tidal heating. The same process heats Jupiter's moon Io, making it the most volcanically active body in the solar system. For a rocky circumbinary planet, tidal heating could be significant. If the planet has a molten interior, the tidal forces could drive vigorous convection, powering plate tectonics and maintaining a magnetic field, both important for habitability. On the other hand, too much tidal heating can be destructive. If the planet orbits too close to the binary, the tidal forces could melt its entire interior, creating a lava world. Or, in extreme cases, the tidal forces could exceed the planet's structural strength, literally tearing it apart. This is called the Roche limit, the minimum distance at which a celestial body can orbit without being pulled apart by tidal forces. For circumbinary planets, the effective Roche limit depends on both stars' masses and the planet's own structural properties. All the circumbinary planets we've discovered orbit well beyond their system's Roche limits, so they're in no danger of tidal disruption. But it's a factor that constrains how close these planets can form or migrate. Now, let's explore the lighting geometry, the patterns of light and shadow that make circumbinary planets so visually spectacular. Imagine you're standing on the surface of a circumbinary planet. The planet is rotating, so the stars rise and set. But unlike on Earth, where the sun rises in the east and sets in the west in a predictable arc, the two stars follow more complex paths. If the binary orbit is circular and in the same plane as the planet's equator, the two stars rise and set together, separated by a fixed angle in the sky. Their paths across the sky are parallel arcs. But if the binary orbit is elliptical, the stars' apparent separation changes over time. When they're at the closest point in their mutual orbit, peristron, they appear close together in the sky. When they're at their farthest separation, apastron, they appear far apart. From the planet's surface, you'd see the stars move relative to each other over the course of the binary orbital period. Some days, they'd rise nearly together. Other days, one would rise hours after the other. And then there are eclipses. From the planet's perspective, eclipses occur when one star passes directly in front of the other. For a binary like Kepler 16, where the orbital plane is nearly edge-on to the planet, eclipses happen every binary orbital period, every 41 days. During a primary eclipse, the larger star is eclipsed by the smaller star. The combined light from the system drops by about 10% depending on the size ratio of the stars. During a secondary eclipse, the smaller star is eclipsed by the larger star. The light drop is smaller, maybe a few percent, because the smaller star contributes less light. From the surface of the planet, you'd see one sun passing in front of the other, a spectacular double sun eclipse. The sky would dim noticeably. Shadows would shift and merge as one light source is temporarily blocked. These eclipses would be regular and predictable, occurring at the same phase of the binary orbital cycle. Ancient civilizations on such a world would have tracked these eclipses, built calendars around them, perhaps even worshipped them as divine events. Now, let's think about seasonal variations. On Earth, seasons are caused by axial tilt. Earth's axis is tilted 23.5 degrees relative to its orbital plane, so as we orbit the Sun, different hemispheres receive more direct sunlight at different times of year. A circumbinary planet with axial tilt would have similar seasons, but complicated by the binary orbital cycle. Let's say the planet's year is 229 days, like Kepler 16b, and the binary period is 41 days. As the planet orbits, it goes through about 5.6 binary periods per year. If the planet's northern hemisphere is tilted toward the binary during the binary's bright phase, when both stars are contributing maximum light, that hemisphere experiences an enhanced summer, hotter and brighter than usual. But 6 months later, when the northern hemisphere is tilted away, creating winter, if that coincides with the binary's bright phase, the winter is milder than it would otherwise be. The next year, the phase relationship shifts. Maybe summer now coincides with the binary's dim phase, making it cooler. Winter might coincide with the dim phase too, making it colder. Over several years, all possible phase combinations occur. The exact seasonal pattern repeats only when the planet's orbital period and the binary period come back into the same phase relationship, a process that might take a decade or more. For inhabitants of such a world, predicting weather and climate would require tracking multiple cycles simultaneously. Farmers would need to know not just the season, but also where the binary is in its cycle to predict temperature and rainfall patterns. This complexity might sound like a challenge, but it could also drive scientific and mathematical development. Civilizations on circumbinary planets might develop sophisticated astronomy and mathematics earlier than Earth civilizations did, simply because they needed it to survive. Let's also consider how radiation from two stars affects the planet's climate. On Earth, the sun's radiation drives all weather and climate. Sunlight heats the surface unevenly, more at the equator, less at the poles, creating temperature gradients that drive wind, ocean currents, and weather systems. On a circumbinary planet, you have two radiation sources. If the stars have different temperatures and luminosities, like Kepler 16's orange primary and red secondary, they emit different spectra of light. The primary might emit more visible light, while the secondary emits proportionally more infrared. Plants evolving on such a world might have pigments adapted to absorb light from both spectra, giving them unusual colors compared to Earth plants. The combined radiation creates a more complex heating pattern. When both stars are above the horizon, the heating is intense. When only one star is visible, the heating is moderate. When both are below the horizon, night, the planet cools. But because the stars don't set simultaneously, true night, when both stars are below the horizon, might be brief or non-existent in some seasons, depending on the planet's axial tilt and orbital position. This could create unique climate zones. Regions near the equator might experience near constant daylight for parts of the year as one or both stars remain above the horizon. Polar regions might have prolonged periods when one sun is circumpolar, circling the sky without setting, while the other rises and sets normally. The climate models for such worlds are complex, requiring sophisticated simulations that account for the dual radiation sources, the variable heating patterns, and the feedback effects of atmosphere and oceans. Scientists have run preliminary models for circumbinary planets in habitable zones. The results suggest that with the right atmospheric composition, greenhouse gases like CO2 and water vapor to trap heat, these planets can maintain stable climates despite the variability in radiation. In fact, the variability might help stabilize the climate. Variations in heating drive stronger atmospheric circulation, which redistributes heat more efficiently from hot regions to cold regions. This could make circumbinary planets more resistant to runaway greenhouse or icehouse effects compared to single-star planets. It's early days for these models, but the preliminary results are encouraging. Circumbinary planets might not just be habitable. They might be particularly good at maintaining stable, life-friendly climates over long timescales. We've focused mostly on circumbinary planets themselves, but let's expand our view. In a binary star system, planets aren't the only objects that can exist. There are moons, asteroid belts, Trojan asteroids, and potentially exotic configurations that we haven't fully explored. Let's start with moons. In our solar system, most gas giants have extensive moon systems. Jupiter has 95 known moons. Saturn has 146. Some of these moons are geologically active, with subsurface oceans, volcanic activity, and complex chemistry. If circumbinary gas giants like Kepler 16b have similar moon systems, those moons could be fascinating worlds in their own right. A moon orbiting Kepler 16b would experience an even more complex environment than the planet itself. The moon is gravitationally bound to the planet, orbiting it every few days to weeks. But the planet is orbiting the binary, and the binary stars are orbiting each other. From the moon's surface, you'd see the gas giant dominating the sky, much like Jupiter appears from the perspective of its moons. But the giant planet wouldn't appear stationary. It would go through phases, lit by the two suns that move behind and around it. When the planet is between the moon and the suns are hidden, a planetary eclipse. The sky would darken, and you'd see the illuminated edge of the planet's atmosphere glowing like a ring around its silhouette. When the moon is between the planet and the suns, you'd see the planet fully lit, and beyond it, the two suns moving relative to each other. The lighting and heating patterns would be extraordinarily complex. The Moon receives direct radiation from the two suns, but also reflected and re-radiated heat from the planet. Depending on the Moon's orbital position, it might be bathed in sunlight, in planetary shadow, or illuminated by light reflecting off the planet's clouds. This complexity could actually be beneficial for habitability. The planet provides a heat buffer, re-radiating warmth even when the suns are eclipsed or during the dim phases of the binary cycle. This could help stabilize the Moon's temperature, preventing extreme swings between hot and cold. Additionally, if the Moon is tidally locked to the planet, always showing the same face to it, like Earth's Moon is to Earth, then one hemisphere always faces the planet, while the other faces away. The planet-facing side receives reflected light and heat, while the far side experiences more extreme day-night cycles. This creates distinct climate zones that could drive interesting atmospheric and geological processes. For a Moon to be habitable, it needs several things. It must be large enough to retain an atmosphere, at least as large as Mars, ideally closer to Earth's size. It needs geological activity to recycle atmospheric gases and maintain a magnetic field if possible. And it must orbit within the binary system's habitable zone. Kepler 16b orbits within its system's habitable zone, so any sufficiently large moon it might have could potentially be habitable. The same is true for other circumbinary planets in habitable zones. We haven't detected any exomoons yet, moons around planets in other star systems. They're too small for current technology to detect via transits or other methods, but future telescopes might be able to detect them, especially large moons around circumbinary planets. If we find an Earth-sized moon or orbiting a gas giant in a circumbinary habitable zone, it would instantly become one of the most interesting targets in the search for extraterrestrial life. Now let's talk about Trojan asteroids. Trojans are objects that orbit in stable points called Lagrange points, locations where the gravitational forces of two bodies balance in specific ways. In our solar system, Jupiter has large groups of Trojan asteroids that orbit 60 degrees ahead of and behind Jupiter in its orbit around the Sun. These are called the L4 and L5 Lagrange points. Objects in these locations are in stable orbits, maintained by the balance between the Sun's gravity, Jupiter's gravity, and the centrifugal force from their orbital motion. In a binary star system, there are multiple sets of Lagrange points. There are points where the gravity of the two stars balance, and there are points where a planet's gravity and the binary's gravity balance. Could asteroids or even small planets exist in the Lagrange points of circumbinary systems? The answer is maybe, but it's complicated. The L4 and L5 Lagrange points in a binary system are less stable than in a single star system because of the time-varying gravitational field. The stability depends on the mass ratio of the stars and the eccentricity of their orbits. For some binaries, the Lagrange points are stable over long timescales, and we'd expect Trojans to accumulate there. For others, the points are only temporarily stable, and any objects there would eventually drift away. We haven't observed Trojan populations in circumbinary systems yet. Again, they are too faint for current detection methods, but as observational techniques improve, we might find them. If they exist, Trojan asteroids in circumbinary systems could be important. They'd be reservoirs of volatile materials, water ice, organic compounds, that could be delivered to planets via impacts, seeding them with the building blocks for life. Now let's talk about exotic orbital configurations. Most circumbinary planets we've discovered have relatively simple orbits, roughly circular, roughly aligned with the binary orbital plane, but in principle, more exotic configurations are possible. For example, a planet could have a polar orbit, one that passes over the poles of the binary system rather than orbiting in the same plane. Such orbits are generally less stable, but under certain conditions, they can persist for long periods. From the surface of a planet in a polar orbit, the view would be surreal. The two stars would appear to rotate around the sky in a tilted plane, sometimes both above the horizon, sometimes both below, creating day-night cycles completely unlike any other configuration. Another exotic possibility is a retrograde orbit, a planet orbiting in the opposite direction to the star's mutual orbit. Retrograde orbits are even less stable than polar orbits, but they're not impossible. And then there's the idea of horseshoe orbits. In our solar system, some asteroids have horseshoe orbits relative to Earth. They orbit the Sun in nearly the same path as Earth, but slightly slower or faster. Over time, they drift closer to Earth, get gravitationally nudged, and switch to orbiting slightly faster or slower, creating a horseshoe-shaped path relative to Earth. In a binary system, planets or large asteroids could potentially have horseshoe orbits relative to each other, or relative to the Lagrange points. These exotic configurations are mostly theoretical. We haven't observed them yet. But the mathematical and dynamical analysis suggest they're possible under specific conditions. The diversity of potential orbital configurations in binary systems is vast, far greater than in single-star systems. This means that as we discover more circumbinary systems and study them in greater detail, we're likely to find unexpected and surprising arrangements. Let's also consider the long-term evolution of circumbinary systems. Over millions and billions of years, the orbits of planets, moons, and asteroids slowly change due to tidal interactions, gravitational perturbations, and other effects. In single-star systems, this evolution is relatively predictable. Tidal forces cause moons to slowly drift away from or toward their planets. Gravitational interactions between planets can cause their orbits to shift over time. In binary systems, the evolution is more complex because of the additional gravitational influences from the two stars. Planets can migrate inward or outward due to interactions with the disk during the early stages, as we discussed before. But even after the disk is gone, long-term perturbations can cause orbital changes. For example, if a circumbinary planet's orbit is slightly eccentric, the binary's gravity can slowly pump up that eccentricity over millions of years, eventually destabilizing the orbit. Or conversely, tidal forces can damp eccentricity, circularizing the orbit. These processes determine the long-term habitability of circumbinary planets. A planet might be in the habitable zone today, but if its orbit is slowly evolving toward instability, it might not remain habitable for the billions of years required for complex life to evolve. Understanding the long-term stability of circumbinary orbits requires sophisticated simulations run over billions of orbital periods. Astronomers are actively working on this, trying to determine which configurations are truly stable over geological timescales and which are only temporarily stable. The preliminary results suggest that most of the circumbinary planets we've discovered are in stable configurations that should persist for billions of years. Their orbits are well beyond the instability threshold, and their eccentricities are low enough that they won't be pumped up by binary perturbations. This is encouraging for habitability. It means circumbinary planets can provide stable environments for life to evolve over the immense timescales required. But there's a caveat. The stars themselves are evolving. Over billions of years, stars change. They grow brighter as they age, eventually swelling into red giants and then dying. For a circumbinary planet, the evolution of both stars matters. If the stars are similar in mass, they'll evolve on similar timescales, both gradually brightening over billions of years. This shifts the habitable zone outward over time. A planet that's in the habitable zone today might become too hot in a few billion years as the stars brighten, or a planet that's currently too cold might become habitable in the future. In binary systems where the stars have different masses, like Kepler 16 with a K-type primary and M-type secondary, the stars evolve at different rates. The more massive primary will evolve faster, brightening and eventually leaving the main sequence while the smaller secondary is still stable. This creates a complex evolutionary environment. The habitable zone shifts over time, not in a simple outward drift but in a more complicated pattern, as the two stars contribute different amounts of light at different stages of their evolution. For life to survive these changes, it needs to be adaptable, or the planet needs to be in a location where it remains habitable throughout the star's main sequence lifetimes. All of these factors, moons, trojans, exotic orbits, long-term stability, stellar evolution, add layers of complexity to understanding circumbinary systems. Each layer reveals new possibilities and new challenges for habitability and the existence of life. And each layer reminds us that the universe is far more intricate than our simple models suggest. Nature doesn't follow the neat categories we create. It finds solutions in unexpected places, creates stability in seemingly chaotic environments, and perhaps nurtures life in conditions we're only beginning to understand. We've explored the physics, the planets, the possibilities. Now let's confront the big question head-on. Could life exist on a circumbinary planet? And if so, how would we detect it? This is one of the most profound questions in modern science. The search for extraterrestrial life drives much of astronomy today. We've sent rovers to Mars, probes to the icy moons of Jupiter and Saturn, and we're building telescopes specifically designed to search for biosignatures in exoplanet atmospheres. Circumbinary planets add a new dimension to this search. If life can exist under two suns, then the number of potential life-bearing worlds in the galaxy increases dramatically. Let's start with the basics. What does life need? At minimum, life as we know it requires three things: liquid water, an energy source, and organic chemistry. Liquid water is the universal solvent. It's where the complex chemistry of life occurs. Water molecules have unique properties. They can dissolve a wide range of substances. They remain liquid over a large temperature range, and they're abundant in the universe. An energy source drives the metabolism of living organisms. On Earth, most life ultimately depends on sunlight, either directly through photosynthesis or indirectly by consuming organisms that photosynthesize. But life can also use chemical energy, geothermal heat from volcanic vents, chemical reactions between minerals and water. Organic chemistry, the chemistry of carbon compounds, provides the structural basis for life. Carbon can form long chains and complex molecules, creating proteins, DNA, lipids, and all the other molecules life uses. A circumbinary planet in the habitable zone could, in principle, provide all three. If the planet has liquid water oceans, an atmosphere, and receives radiation from two stars, the basic ingredients are there. But let's dig deeper. What specific challenges and opportunities does the circumbinary environment present? Challenge 1. Radiation variability. As we've discussed, the light and heat a circumbinary planet receives varies due to the binary orbital cycle. Plants on Earth are adapted to daily and seasonal cycles, but the variations are predictable and relatively stable. On a circumbinary planet, the variations are more complex. Could photosynthetic organisms adapt to multi-period light cycles? Could they store energy during bright phases to survive dim phases? The answer is probably yes. Plants on Earth already have mechanisms to cope with variable light. They can adjust photosynthesis rates, store energy as starches and sugars, and go dormant during unfavorable periods. Circumbinary plants might evolve more sophisticated versions of these mechanisms. They might have biological clocks that track multiple cycles, anticipating both the daily rotation and the binary orbital variations. Or they might be generalists, capable of photosynthesizing across a wide range of light intensities and spectra, not finely tuned to specific conditions like some Earth plants are. Challenge 2. Spectral differences. The two stars in a binary system likely have different temperatures and thus different spectra. One might emit more blue light, the other more red light. Earth plants are green because they reflect green light. They absorb red and blue wavelengths for photosynthesis. This is optimized for our Sun spectrum, which peaks in the visible range. Circumbinary plants might need to absorb light across a broader range of wavelengths to capture energy from both stars efficiently. This could give them unusual colors, black, purple, or metallic hues that absorb a wide spectrum. Or there might be multiple types of photosynthetic organisms, each specialized for one star's spectrum, coexisting in different niches. This spectral diversity could actually drive biological diversity. Different wavelengths penetrate to different depths in water or canopy, creating ecological zones where different types of photosynthesizers thrive. Challenge 3. Climate variability. We've talked about the complex seasonal patterns on circumbinary planets. Could ecosystems adapt to multi-year cycles where the severity of seasons varies unpredictably from year to year? On Earth, some ecosystems experience high variability. Deserts where rainfall is unpredictable, polar regions where climate varies with long-term solar cycles. Life in these environments is adapted to cope with uncertainty, using strategies like long lifespans, seed banks that germinate only when conditions are favorable, or migration to follow resources. Circumbinary ecosystems might rely heavily on similar strategies. Life might be long-lived, capable of surviving through multiple unfavorable cycles, or it might reproduce rapidly when conditions are good, creating resilient populations that can withstand periodic die-offs. The key point is this: while circumbinary environments are more variable than Earth's, the variability isn't random. It follows predictable patterns, albeit complex multi-period patterns. And if the variability is predictable, life can adapt to it. Now let's talk about opportunities. What advantages might circumbinary environments offer for life? Opportunity 1. More total energy. 2 stars provide more combined radiation than one, even if each star is individually dim. This could support higher productivity, more photosynthesis, more biomass, richer ecosystems. Opportunity 2. Environmental diversity. The complex light patterns, shadow zones, and twilight regions create diverse ecological niches. On Earth, diversity of niches drives diversity of life. The same could be true on circumbinary planets, potentially leading to more biologically diverse ecosystems than on single-star planets. Opportunity 3. Tidal heating and geological activity. The time-varying tidal forces from the binary could maintain geological activity, volcanism, plate tectonics, over longer timescales than on single-star planets. Geological activity is important for habitability because it recycles nutrients, regulates atmospheric composition, and drives the chemical cycles that life depends on. So, could life exist? The scientific consensus is yes, it's plausible. Not certain, but plausible. The challenges are real, but none of them appear insurmountable. If life exists on circumbinary planets, the next question is, how would we detect it? The primary method for detecting life on exoplanets is through biosignatures, atmospheric gases or surface features that indicate biological activity. On Earth, the most obvious biosignature is oxygen. Earth's atmosphere is 21% oxygen, and this oxygen is produced by photosynthetic organisms. Without life constantly replenishing it, atmospheric oxygen would react with rocks and disappear within a few million years. If we detect significant oxygen in an exoplanet's atmosphere, especially in combination with other gases like methane that don't coexist in equilibrium, it's a strong hint of life. But detecting atmospheric composition requires spectroscopy, analyzing the light that passes through or reflects off a planet's atmosphere. This is incredibly challenging for distant exoplanets, especially small rocky ones. For circumbinary planets, there are additional challenges. The planet's signal is mixed with light from 2 stars, not one. Separating the planet's faint atmospheric signal from the star's bright light is harder. Additionally, transits of circumbinary planets are often grazing or partial because of the complex orbital geometry. This reduces the signal strength, making atmospheric detection even more difficult. Despite these challenges, the James Webb Space Telescope is capable of studying the atmospheres of some circumbinary planets. JWST has already begun characterizing exoplanet atmospheres in single-star systems, detecting water vapor, CO2, methane, and other gases. For larger circumbinary planets like Kepler 16b, JWST could potentially detect atmospheric gases, though these gas giants are unlikely to host life. For smaller circumbinary planets in habitable zones, like Kepler 47c, atmospheric characterization is more challenging, because they're smaller and farther from their stars. But it's not impossible. If JWST observes enough transits, it could build up enough signal to detect major atmospheric components. In the future, more advanced telescopes will be needed to detect biosignatures in the atmospheres of Earth-sized circumbinary planets. The Habitable Worlds Observatory, a proposed NASA mission, is specifically designed for this purpose. This telescope would use a star shade to block light from the stars, allowing direct imaging and spectroscopy of planets. For circumbinary systems, this is more challenging because there are 2 stars to block, not 1, but it's technically feasible with advanced star shade designs. If such a mission is built and launched, probably in the 2040s, it could potentially detect oxygen, methane, water vapor, and other biosignatures in the atmospheres of circumbinary planets. But biosignatures aren't the only way to detect life. Surface features can also indicate biology. On Earth, vegetation has a distinctive spectral signature. It reflects strongly in the near-infrared, creating the red edge in Earth's spectrum. This is because chlorophyll, the main photosynthetic pigment, reflects infrared light while absorbing visible light. If circumbinary planets have photosynthetic life, they might have similar spectral features. The exact wavelength of the edge might differ because circumbinary photosynthesis could use different pigments adapted to the dual star spectrum. Detecting these surface biosignatures requires direct imaging of the planet, seeing it as a point of light separate from its stars. This is even more challenging than the atmospheric spectroscopy, but future telescopes might be capable of it for nearby circumbinary systems. There's also the possibility of detecting technosignatures, signs of technological civilizations. If intelligent life evolved on a circumbinary planet and developed technology, they might emit radio signals, laser pulses, or other forms of deliberate or inadvertent electromagnetic radiation that we could detect. They might also engineer their environment in detectable ways, constructing massive structures, altering atmospheric composition, or creating patterns of light on their planet's night side, city lights. SETI, the search for extraterrestrial intelligence, has traditionally focused on stars similar to our Sun. But there's growing interest in searching binary systems too, recognizing that these systems could host habitable worlds. Several SETI surveys now include binary stars in their target lists, listening for signals that might indicate technological civilizations on circumbinary planets. So far, nothing has been detected, but the search is ongoing, and every null result narrows down the possibilities, helping us understand how common or rare life, especially intelligent life, might be. The search for life on circumbinary planets is in its infancy. We've only known these planets exist for about a decade. The tools to study their atmospheres and surfaces in detail are only now becoming available. But the potential is enormous. If we find life on a circumbinary planet, even simple microbial life, it would revolutionize our understanding of biology and our place in the universe. It would prove that life can adapt to conditions radically different from Earth. It would suggest that life is robust, flexible, and potentially common throughout the galaxy. And if we find intelligent life, the implications are even more profound. Contact with a civilization that evolved under 2 suns with different rhythms and cycles than ours would be transformative. Their science, their culture, their perspective on the universe, all would be shaped by their unique environment. It's a long shot, of course. The odds of detecting life, let alone intelligent life, in the near future are low, but the odds aren't zero, and the stakes, understanding our cosmic context, learning whether we're alone, are high enough to justify the effort. So we search, we build better telescopes, we study more circumbinary systems, we listen for signals, and we wait with a mixture of patience and anticipation for the universe to reveal its secrets. We've journeyed through the science, the discovery, the implications of circumbinary planets. But now, in these final moments, I want to step back and share something that, to me, is the most profound revelation of all. Circumbinary planets aren't just curiosities, they're a mirror. They reflect back to us a fundamental truth about the universe, one that changes how we should think about everything. For most of human history, we assumed our solar system was typical. One star, planets in orderly orbits, predictable cycles. When we imagined other worlds, we imagined them as variations on this theme, maybe with different numbers of planets, different sizes, but fundamentally similar. Even when we started discovering exoplanets in the 1990s, we clung to this assumption. Yes, we found hot Jupiters and super-Earths, but we assumed these were exceptions, oddities that formed under unusual circumstances. Then we discovered circumbinary planets. And suddenly we realized our solar system isn't typical. It might not even be common. Half of all stars are in binary or multiple systems. If circumbinary planets are common around these stars, and the evidence suggests they are, then there are potentially billions of such worlds in our galaxy alone. This means that a significant fraction, perhaps even the majority of planets in the universe experience conditions utterly unlike Earth. Dual suns, complex light cycles, twilight zones, multi-period seasons. For life on these worlds, if it exists, these conditions aren't exotic or strange. They're normal. They're home. And this flips our perspective. Instead of thinking of single-star systems like ours as the default, with binary systems as variations, we should think of planetary systems in general as a spectrum. Single-star systems are one end, binary systems are another. And there are multiple star systems with 3, 4, or more stars, each creating even more complex environments. We live in one small corner of this spectrum, and from that corner, we've been trying to understand the whole universe. But here's the mind-blowing part. If circumbinary planets are common, and if some of them are habitable, and if life is robust enough to emerge and thrive in these environments, then we have to confront an astonishing possibility. There might be more life in the universe adapted to 2 suns than to 1. Let that sink in. Life under binary stars might be more common than life under single stars. If that's true, then normal life in the galaxy doesn't look like us. It looks like something adapted to twilight zones, multi-period cycles, and dual star spectra. We're not the template. We're the exception. This is humbling. Profoundly humbling. Because it means our entire framework for thinking about life, based on Earth's environment, adapted to a single sun, might be a narrow, limited perspective. When we search for habitable planets, we look for Earth-like worlds. But maybe we should be looking for Kepler 47-like worlds. Maybe we should be prioritizing binary systems, because that's where the majority of habitable real estate actually exists. And if we ever do make contact with extraterrestrial life, there's a decent chance it evolved on a circumbinary planet. Its biology, its perception of time, its culture, all shaped by rhythms and cycles we don't experience. Imagine trying to communicate with such a civilization. We count time in days and years. They might count time in binary cycles, planetary years, and the complex beat frequencies where the 2 cycles align. We evolved under a sky with 1 sun and 1 moon. They might have evolved under a sky with 2 suns and a gas giant parent planet going through phases. Our entire cognitive framework, how we perceive time, light, causality, is rooted in Earth's environment. Theirs would be completely different. But here's the beautiful part. Despite these differences, the fundamental laws of physics, chemistry, and mathematics would be the same. A civilization on a circumbinary planet would discover the same laws of motion, the same quantum mechanics, the same periodic table. Science is universal. It transcends environment and biology. And that universality is what would allow us to communicate, to share knowledge, to understand each other despite our differences. This brings me to the deeper philosophical point. Circumbinary planets remind us that the universe is not designed for us. It's not centered on us. It doesn't conform to our expectations. The universe simply is. It follows physical laws, and those laws allow for an extraordinary diversity of outcomes. Single-star systems, binary systems, circumbinary planets, endless twilight zones. All of it is natural. All of it is physics playing out. We happen to live in one configuration, but it's just one among countless possibilities. And yet, despite this vast diversity, we can understand it. With telescopes and mathematics, with patience and ingenuity, we can study worlds we'll never visit, understand conditions we'll never experience, and grasp the physics that governs realities completely unlike our own. That's the true miracle. Not that the universe is comprehensible, but that we, these collections of atoms on a tiny rock orbiting a single ordinary star, can comprehend it. Circumbinary planets are a testament to the universe's creativity. They're worlds that shouldn't exist according to our early theories, but which nature created anyway. They're environments that challenge our assumptions about habitability, yet which might host thriving ecosystems. They're a reminder that the cosmos is far larger, stranger, and more wonderful than we ever imagined. And they're an invitation. An invitation to keep exploring, keep questioning, keep pushing the boundaries of our knowledge. Because for every answer we find, for every mystery we solve, the universe reveals new questions, deeper puzzles, more profound enigmas. The discovery of circumbinary planets opened a new chapter in astronomy. But it's just one chapter. There are others waiting to be written about worlds orbiting pulsars, planets in triple star systems, rogue planets drifting through interstellar space, and configurations we haven't even conceived of yet. Each discovery expands our understanding. Each one shifts our perspective. And each one reminds us that we're part of something vast and ancient. We're made of atoms forged in dying stars, living on a planet orbiting an unremarkable star, in a galaxy containing billions of other stars and planets. We're tiny, insignificant on cosmic scales, but we're also extraordinary because we can look up at the night sky, point our telescopes at distant points of light, and discover worlds with two suns. We can understand the physics that governs them. We can imagine what life might be like under alien skies. We're the universe becoming aware of itself. We're matter arranged in such a way that it can contemplate matter. And right now, somewhere out there, 40 light years away, Kepler 16b is completing another orbit around its binary stars. The stars are eclipsing each other, as they have for millions of years, as they will for millions more. The planet doesn't know we've discovered it. It doesn't care about our theories, our debates, our wonder. It simply exists, a world of twin suns and endless twilight, governed by the same physics that governs everything, shaped by forces that care nothing for our imagination. But we know it's there. We've seen its shadow. We've measured its orbit. We've calculated its temperature and pondered its moons. And in knowing it, we've changed ourselves. We've expanded our sense of what's possible. We've taken another step toward understanding the full scope of cosmic reality. That's the gift of circumbinary planets. Not just scientific knowledge, but a shift in perspective. A reminder that the universe is larger than our experience, stranger than our assumptions, and more beautiful than our imaginings. And the journey has only begun. And so we come to the end of our exploration. 2 hours journeying through the science, the mystery, and the profound implications of circumbinary planets. Worlds with two suns, where twilight stretches across continents, and the sky tells stories in dual shadows. Let's recap what we've covered, because this has been a vast expedition through planetary science, orbital mechanics, habitability, and the search for life. We started with the discovery of Kepler 16b in 2011, the moment astronomers confirmed that planets can orbit binary stars, defying decades of theoretical predictions that said such worlds were impossible. We learned how the Kepler Space Telescope detected this planet through transits, watching it pass in front of its two stars, creating a telltale dimming pattern. We explored the nature of binary stars themselves, how they form, how they orbit each other, and why they're so common in our galaxy. Nearly half of all sun-like stars exist in binary or multiple systems, which means the potential for circumbinary planets is enormous. We dove deep into orbital mechanics and the three-body problem, understanding why circumbinary orbits are stable only beyond a critical distance from the binary pair, and why the planets we've discovered cluster just outside this stability boundary. We imagined what it would be like to experience life on such a world. The double sunrises, the complex shadows, the multi-period seasonal cycles that repeat only after several years. We contemplated the twilight zones, regions where one sun is always visible while the other rises and sets, creating perpetual intermediate lighting that might be the most habitable regions on these worlds. We investigated how circumbinary planets form, exploring the challenges of planet formation in the gravitationally chaotic environment of a binary system, and the possible migration scenarios that could explain their current positions. We toured the dozen-plus circumbinary planets we've discovered so far, from Kepler 16b to Kepler 47c to TOI 1338b, each one unique, each one expanding our understanding of what's possible. We examined the habitability question, asking whether life could adapt to the variable radiation patterns, complex seasonal cycles, and dual star spectra of circumbinary environments. The answer? It's plausible. The challenges are real, but none appear insurmountable, and circumbinary planets might even offer advantages for life in some ways. We discussed moons, trojans, and exotic orbital configurations, recognizing that circumbinary systems might host even more diversity than we've yet discovered: moons of gas giants that could be habitable, Trojan asteroids at Lagrange points, polar or retrograde orbits that create truly alien sky patterns. We explored how we might detect life on these worlds, through atmospheric biosignatures, surface features, or even technosignatures from intelligent civilizations that evolved under binary stars. And finally, we confronted the profound implication that circumbinary planets might represent a common, perhaps even dominant, type of planetary environment in the galaxy. That life adapted to two suns might be more common than life adapted to one, that our single-star solar system might be the exception, not the rule. This shifts our entire perspective on our place in the universe. We're not at the center. We're not the template. We're one outcome among countless possibilities, living in one configuration among infinite variations, but we're also extraordinary. Because despite being this one small outcome, we can understand all the others. We can discover worlds we'll never visit, comprehend physics we'll never directly experience, and imagine life in forms we'll never encounter. That's the power of science. That's the triumph of human curiosity. Now I want to hear from you, because this isn't just me talking to you. This is a conversation that extends into the comments, into the community of curious minds that make this channel what it is. What struck you most about circumbinary planets? Was it the complex orbital mechanics, the possibility of life under two suns, the twilight zones where neither full day nor full night exists, the philosophical implications of discovering that our solar system might be atypical? Do you think life could really adapt to the conditions on these worlds? If so, what do you imagine it would look like? What adaptations would be necessary? And here's a fun thought experiment. If you could visit any of the circumbinary planets we've discussed, Kepler 16b's moons, Kepler 47c, or another, which would you choose and why? I read every comment, your insights, your questions, your speculations. They enrich these explorations for everyone. So please, share your thoughts, challenge assumptions, ask the questions I didn't address. That's how we all learn together. If you found value in this deep dive, I have a few requests that help this content reach more people who might find the same sense of wonder you hopefully experienced. First, subscribe to the channel if you haven't already, and hit the notification bell. There are so many more cosmic mysteries to explore, from planets orbiting 3 stars, to the strange worlds around pulsars, to the possibility of life in the clouds of Venus. Each video is crafted with the same depth and care, designed for people who want to truly understand the universe. Second, give this video a thumbs up. It signals to the algorithm that this content resonates, helping it reach others who love space and science. Third, share this video. Send it to a friend who wonders about other worlds, post it in communities of space enthusiasts, recommend it to someone looking for something thought-provoking and inspiring. The more minds we reach, the larger our community of cosmic explorers becomes. And fourth, check out the other videos on the channel. Every exploration is a journey into wonder, into the strange and beautiful reality we inhabit. Before we part, I want to leave you with one final image. Right now, at this very moment, somewhere among the stars, a circumbinary planet is completing its orbit. 2 suns are rising over its horizon, casting intertwined shadows across landscapes we've never seen. Perhaps there's an ocean, waves glittering with dual reflections. Perhaps there's a moon in the sky, illuminated by both stars simultaneously. Perhaps there's life, microbes in the ocean, forest covering the continents, maybe even someone standing on a shore, looking up at their 2 suns and wondering if they're alone in the universe. We don't know if such a scene exists, but the physics allows for it. The planets are out there, the conditions could be right, And that possibility that somewhere under twin suns life might be pondering the same questions we are is enough to keep us searching, keep us wondering, keep us exploring. Because the universe is vast, but it's not empty. It's filled with stars and planets, with possibilities and potentials. And every discovery we make, every world we find, brings us closer to understanding the full scope of reality. We live in an age of discovery, an age where we can detect planets around other stars, study their atmospheres, and search for signs of life. An age where the impossible becomes possible, where theoretical predictions give way to observed reality. Future generations will look back on this era the way we look back on the age of oceanic exploration, when humans first circumnavigated the globe and mapped distant continents. They'll see us as pioneers, charting the cosmic ocean, discovering new worlds, and among those worlds the circumbinary planets will hold a special place. They're the worlds that taught us our assumptions were too narrow, that showed us nature's creativity exceeds our imagination, that proved once again that the universe is stranger and more beautiful than we dared believe. Thank you for joining me on this journey. Thank you for your time, your attention, your curiosity. Keep looking up, keep questioning, keep wondering, because somewhere out there, under skies lit by two suns, the universe is waiting to be discovered, and the adventure has only just begun.